Hey, welcome to Tricksaw. Today we'll be talking about how time and motion comes into play in calculus. It all happens with vector-valued functions. So to start off, what is a vector? Well, a vector is a function that holds multiple components. An example of this could be, let's say we have a vector r. And let's give r two components, an x component, x of t, and a y component, y of t. And vectors can have as many components as you want. You could add a third component, z of t, if you want to. But for now, we'll just stick with two components, the x and the y components. But now, what are components? Well, components are just functions of their own. For example, x of t could just be t squared, or y of t could be cosine of t. But what's the use of a vector? Well, in this case, this is a two-dimensional position vector that evaluates position with time, and that's where time comes in. T is equal to time. And so you could say, as time passes, the x value position of the vector is x of t, and the y position evaluated with time is y of t. So this vector can hold two-dimensional position data. But you don't only have to have position vectors. You can also have a velocity vector. Let's say you have a vector v of t, and you still want to keep it two-dimensional. So you want to have two components. You want to have an x component velocity and a y component velocity. So you could create a vector v. You could do v sub x of t, and you can do v sub y of t. So what does this mean now? Well, if we want to keep these vectors with the same object, you could say that this is the same vector, but it's talking about the velocity instead of the position. And if you've taken any physics class, you know that velocity is the derivative of the position. So you could say that the velocity in the x side is 2t, and the velocity in the y side is negative sine of t. And how do I know this? Well, a very important rule of vectors is that if you want to differentiate one, you can just differentiate each separate component, and it works. So over here, you can go from a position vector to a velocity vector by deriving it. Deriving with respect to time, d dt. And you could go another step. You can make an acceleration vector. We could do an acceleration vector a is equal to, well, what would the acceleration component in the x direction be? Well, it would be the derivative. So we have a sub x of t, and we have a sub y of t. And from deriving each side, what would we get? Well, if you take in physics, you know acceleration is the derivative of velocity. So the x component of the acceleration would be 2, and the y component of acceleration would be the derivative of negative sine of t, so it would be negative cosine of t. And you can go on and on, but the main spheres of motion we talk about is position, velocity, and acceleration. Now let's talk about the next level of motion in calculus: speed, distance, and displacement. So let's say we have a velocity vector. V is equal to v sub x of t and v sub y of t. So what is speed? So speed and velocity is not the same thing, because speed is a scalar value, means it has no direction, so it always must be a positive value. Well, speed is just the magnitude of the velocity. So speed is equal to the square root of v sub x of t squared plus v sub y of t squared. And now we can start combining this concept of motion and calculus with integral calculus. So distance is the integral of speed. And we know whenever we want a definite integral, we have to have a starting point and an ending point. Well, what makes this interesting is we can integrate with time. We can have a starting time and we can have an ending time, time 1 and time 2, and we can integrate the speed. So the square root of v sub x of t squared plus v sub y of t squared. So what does this give us? Well, this gives us the total distance traveled by our particle from time 1 to time 2. And so this is distance. It's not displacement, but it's distance. So now if we want to get into displacement, it's very similar, but we can do it with our velocities. It's the same concept of integration. We can integrate from a first time to a second time, but we can do it in one dimension. What if we're finding the total displacement in x? We can integrate just our x velocity. And so what does this give us? Well, this gives us the displacement in x from time 1 to time 2. So this is how we can start thinking about motion and time in calculus. And you could do the same thing, but you could change the x to a y. There's so many applications of this, especially in particle motion. Thanks for watching. This video was really fun to make because it really delves into one of the real-world applications of calculus. We see motion and time all around us, and vector-valued functions are really useful in combining physics and calculus, two really important fields. Thank you for watching. Please consider subscribing. I'll see you in the next video.